Hello, everyone. Welcome to the ILTA Physics online problem-solving lecture. The problem we are going to solve today is about the orbital motion of a satellite. Orbital motion can be described as circular motion on a very large scale. As shown in the figure below, the movement of things like a satellite orbiting a large planet like Earth is a great example of the orbital motion we will study today. The types of problems we will cover today are basic types that solve the orbital motion of a satellite as a circular motion. First, let's summarize the simple theoretical concepts we need. Orbital motion describes the circular motion of small satellites orbiting a large planet. In general, they don't have a perfectly circular trajectory, but we can think of them as moving in a circular path at an approximately constant speed. Specifically, the problem types we are covering today are the basic questions often asked about this kind of orbital motion. In the case of a satellite orbiting a large planet like Earth, as shown in the right figure, the height at which the satellite floats is relatively small compared to the size or radius of the planet. Therefore, although the satellite has a centripetal acceleration for circular motion, we use an approximation that this centripetal acceleration is about the same magnitude as the gravitational acceleration that an object on Earth receives toward the center of the Earth. To put this from another perspective, when a satellite is orbiting an arbitrary planet, if we calculate the centripetal acceleration of the satellite, we can find the gravitational acceleration of that planet. For your reference, I'd like to mention in advance that another way to find the gravitational acceleration on an arbitrary planet is to use Newton's universal law of gravitation, which we will learn in the next chapter. Today, we will think about methods for calculating gravitational acceleration using the centripetal acceleration of circular motion. Let's look at the basic formulas we need once again. Because it is circular motion, there is a centripetal acceleration pointing toward the center of the circle. And there is a tangential velocity in the direction of the tangent to the circular trajectory. Tangential velocity can be calculated as the distance traveled divided by the time interval, and it can be expressed in terms of the period and frequency of the circular motion. By substituting the velocity found here into the centripetal acceleration formula, we can express the centripetal acceleration as a function of the period or frequency. If a question about centripetal force comes up, it can be calculated as the value of the centripetal acceleration we found multiplied by the mass, according to the Newton's second law. If we know the velocity, we use the centripetal acceleration formula involving velocity. If frequency or period is given as a condition, we can calculate it using the modified version of the formula for frequency or period. You'll need to memorize all these formulas one by one. As long as you accurately understand the formula for centripetal acceleration in circular motion, the definition of velocity, and Newton's second law, you can derive all the other formulas using these relationships. It is best to understand first and then solve the problems. Now, let's solve some basic problems on orbital motion. Problem 32 is about the motion of a satellite orbiting the moon. It says the period for this satellite to complete one orbit around the moon is 110 minutes. It asks what the gravitational acceleration on the moon is if we know the radius of the moon. The important condition here is that the satellite is orbiting in an orbit very close to the surface of the moon. With this condition, as explained earlier, the gravitational acceleration of the moon, or the free fall acceleration, can be calculated as the centripetal acceleration when we consider the satellite's motion as circular motion. Since the period of the moon is 110 minutes, it becomes 6,600 seconds when calculated in seconds. The radius of the moon has a value of 1.74 times 10 to the power of 6 meters. The gravitational acceleration is equal to the centripetal acceleration of the satellite. Using the centripetal acceleration formula that can be used when the period is known, the gravitational acceleration is calculated as 1.58 meters per second squared. Since the Earth's gravitational acceleration is 9.8 meters per second squared, we can see through calculation that it has a small gravitational acceleration of about 1/6 in comparison. Problem 33 is about the motion of a satellite orbiting Mars. Here too, it describes the condition that the orbit of the satellite orbiting Mars is very close to the Martian surface. In this problem, it asks to find the period of the satellite when the free fall acceleration is known. The free fall acceleration given as a condition here is equal to the gravitational acceleration. Specifically, if we consider the circular motion of the satellite, it becomes equal to the centripetal acceleration. The radius of Mars has a size of 3.39 times 10 to the power of 6 meters. Again, we use the formula that the gravitational acceleration or free fall acceleration is equal to the centripetal acceleration of circular motion. Specifically, since we are looking for the period, if we use the formula containing the period and substitute the given conditions into the equation, we can calculate that the period of the satellite is 99 minutes. Today, we covered very typical types of problems regarding the orbital motion of satellites. In the case of a satellite orbiting in a low orbit close to the surface of a planet, because the size of the planet is so large, it is a type of problem using the fact that the centripetal acceleration of the satellite's circular motion is equal to the gravitational acceleration or free fall acceleration with which the planet pulls the satellite. That's it for today's lecture. You all did a great job. See you again next time.